Thank you. Thanks a lot for coming to listen again. And thank you for inviting me to come here. So I'll tell you a little bit. We had a long discussion yesterday about the connections between field theory and Monte Carlo, and so today's talk will be about some my latest results in this field. And so Nishita is over here. Maybe many of you have met her. She's my grad student, and John was my ex-grad student, who's now a postdoc in Lausanne with Frederick Mila, and Matt was a postdoc of mine who's now a professor in California State. Okay, so these are my three collaborators. This is the outline of my talk. I'll tell you, about this idea of designer models, designer Hamiltonians. Very briefly, this is just some general discussion, and then I want to show you two examples of these kind of models that we've studied recently. So first of all, I want to tell you why we study these models at all, because they may seem a little unfamiliar. Okay, so let me just give you the big picture. So, I think one of the great successes of both theoretical physics and computational physics is the connection between classical statistical mechanics and quantum field theories. Right? This invention of Monte Carlo algorithms to study the Ising model, and the incredible results about renormalization group applied to field theory. So this is the simplest example is this Ising model and how it connects to 5-4 field theory. And then there are all these interesting, so at one level there's a phase transition in the Ising model, and this was known for a long time. But over the last century, this knowledge has become more and more refined, including this amazing discovery that we sort of mentioned yesterday of conformal invariance, which is at a critical point. There's a lot more symmetry at a critical point than you would naively guess by looking at the lattice model. Okay, so this connection, I think, is both a triumph of computational physics and also just theoretical physics in general. Okay, so development of conformal field theory is definitely a very profound development in theoretical physics, and this is one of my favorite books where this connection is discussed. Okay, so we know this connection, and it exists for classical statistical mechanics models, and the question that we're very, very interested in is how does this connection work for quantum lattice models? So when you don't have classical variables, but you have quantum variables. So we discussed this a bit yesterday, and in many cases this basically goes through. You can just think of this as quantum field theory in one higher dimension, and then proceed exactly as John Cardy tells you to. But in many cases it fails. Okay, and the ways in which it fails is best known in one dimension, and we discussed this in a lot of detail. The classic example is the Heisenberg chain, and again there's this connection to field theory, but the field theory has something unusual, which is a topological term, and we spoke about this, and in fact this is what got Duncan Halliday the Nobel Prize 2 years ago. And so in one dimension, this connection between quantum lattice models and field theories, we realize the field theories are not as simple as the field theories that emerge from classical statistical mechanics. They're more complicated, but this whole thing can be analyzed, and that's because in one dimension there's an amazing array of techniques. There's DMRG, there's conformal field theory, there's bosonization, beta ansatz, and all of these actually played a role in understanding these lattice models. Okay, so in one dimension, I should say, there's also exact diagonalization is very powerful in one dimension. So in one dimension, this connection between quantum lattice models and field theory is on very good footing, very well understood, and again is a very, very important development in our field of condensed matter physics. So now we obviously are interested in what happens beyond one dimension. So remember, classical statistical mechanics you can do in any dimension, and this connection between field theory you can study in 2 dimensions, in 3 dimensions. And so we would like to go beyond one dimension, because these are intellectually very interesting problems. But then all these methods that we have over here, DMRG, CFT, bosonization, beta ansatz, some of them can be applied in 2 dimensions, but they're much weaker. Okay, their strength is very much based in one dimension. And so then the only thing that we're left with that we can do is, of course, we can study some field theory, but the only way we can get exact results on specific lattice models is through quantum Monte Carlo. Okay, so now the problem, as you all know, is that the quantum Monte Carlo suffers from the sign problem. Okay, so it has lots of models have sign problems, And so, but we know that some models don't, and we've already learned amazing things by studying these models. Right? The classic example is a nail ordering of the Heisenberg model in 2 dimensions, and then deconfined criticality, many things that others have spoken to you about, and many other people over here work on. Okay, so we call these designer models, they're simple models of quantum many-body physics. They're sign problem free, and we want models that have interesting physics. Okay, so something new, and I'm going to show you that this is. So first, many people believe that if the model doesn't have a sign problem, it can't have interesting physics. Now we know that's not true. Okay, so it is possible for sign problem free models to have interesting physics. In fact, we know that they can host deconfined critical points. So what else can they host, and how far can we go with this idea? And the goal here is that we can be able to study the connection between quantum field theory with topological terms in dimensions greater than 1. Okay, and this is a sort of unexplored, intellectually very interesting problem, but very hard to solve. And of course, we can make use of this beautiful. So now again, the models we're going to pick, we're going to try and pick them as simple as possible. Sometimes we don't have a choice. We just have to pick. But there's this important idea of universality, which says that actually, if you want to study a phase transition, for instance, we all know that the Ising model can describe the transition in a system of argon atoms at the liquid-gas transition. Okay, and the Ising model has nothing to do with argon atoms, or for that matter, any atomic system. But there's this very powerful idea of renormalization group, which again intimately has to do with the fact that the critical point has a lot more symmetry than the microscopic model. And so many different microscopic models can have the same fixed points. Okay, and so this very important idea of universality makes all this relevant much more than. So we're going to look for models that don't have the sign problem, and we may have to go to some interesting looking models to do that. But the idea is that we're interested in conceptual questions, and we can still use universality. So we're mainly interested in the connection between Monte Carlo simulations and field theory. But of course, the ultimate goal of physics is to understand experiments, and the hope is that through universality, all of these can be understood. Okay, so that's the backdrop. That's just the manifesto, if you like. We have a paper where we wrote the manifesto down. You can read it and see if you also become brainwashed. And then you can join us. But if not, you can just listen to the talk and have some fun. Okay, so the first talk I'll talk is about spin liquids. And okay, so Phil Anderson came up with this incredible idea, which is called the RBB wave function. Okay, so the RBB wave function. So there was an idea that in the benzene ring that Linus Pauling had, which is that you could have a system in which you form bonds, but these bonds fluctuate between 2 configurations in the benzene molecule. But the question is now, when you have a thermodynamic system, whether you can have such quantum fluctuations. Okay, so the simplest situation you can imagine, and this is from a review, this picture is from a review article written recently, is that you have a set of spins, and we often think of spin 1/2 because the simplest. I will go beyond spin 1/2 for the things that I'm interested in, but you can think of this as a spin 1/2 system, and you can imagine a wave function where you have a superposition of infinitely many of these singlet coverings. Okay, so this is called the resonating valence bond. So there's a simpler thing which is also very interesting that can happen, is that these singlets can form a pattern which we call a valence bond solid. Okay, and so you already heard about the valence bond solid in the talks previously, but there's also a possibility, which is the thing that Anderson sort of in 1973 thought about, is that you could have a system in which these singlets fluctuate and don't form a solid. Okay, so this is a very important idea, and this idea, which is sometimes referred to as the spin liquid, has been a driving force for 50 years in our field. Okay, so I'm going to show you today a model which realizes the spin liquid, and it's a very simple model. It's slightly abstract, and I can show you how it connects to various other models that people study. But let me first introduce the model to you. Okay, so the model, you take a lattice, say the triangle, and we'll be interested in particular non-bipolar lattices. So the triangle, we'll mainly talk about Kagome, but imagine you have a triangular lattice. Okay, and so usually when you think of a spin, it points up or down. It has 2 states. But for my discussion, it will be important that the spin has many states. In fact, it has n states. So n will be a parameter for me. And so now if I take, if I have a lattice which has n-side sites, then the Hilbert space, as you all know, has a dimension of n to the n sides. So it's a very large Hilbert space because I can assign colors independently on every lattice site. Okay, so now I'm going to define the following model. I basically take two sites and I define the bond wave function. Okay, so the bond wave function, which I call a singlet, and I'll tell you why it's called a singlet in a second, is 1 on square root of n sum over all the colors of this two sites having exactly the same spin color. Okay, so now this may seem a little abstract. It's not. I'll show you how many models that we know are actually of this form. So, I'll talk about the model in a second. But let's just look at this for n equal to 3. Okay, so for n equal to 3, you have three colors. You have blue, you have green, you have red. And so this simple two-side wave function is blue, blue plus green, green plus red, red. Okay, we'll call this a singlet wave function. I think in more trendy lingo, you might call this the maximally entangled wave function. So you have two local quantum degrees of freedom, and this is the maximally entangled state that you can have between these two. Okay, so the Hamiltonian that I'm going to discuss is very simple. It's a sum of singlet projectors. Okay, so basically now, imagine I have a triangular lattice, and on every bond, I can define these singlets. And then I can say that if the system is in a singlet state on that bond, I'm going to lower its energy by minus j. And if it's not, then it gets an energy 0. Right? So that's called a singlet projector. And I have just a sum of this interaction on all the bonds. Okay, so this is interesting, and I didn't come up with this model completely on my own. There's a history of studying models like this that goes back. I think Ian Affleck first originated it. And I'll tell you what the difference with what I'm doing is. And also Kenji and Naoki have studied this model before. Okay, so any questions about the model? So this is basically so first part of the talk. I just want to talk to you about the phase diagram of this model. Okay, so again, it's a very, very simple model. And I'll maybe just say it quickly again because the whole talk will sort of depend on this, is that you have singlet between two sites, and the singlet is the equal color, it's a superposition of all states with equal color. So remember, when you have two sites, they can have n square different states, because you can make this blue green, you can make this blue red, you can make this blue whatever you like. But the only states that appear on the singlet are when the two sites have equal color. Okay, so let's try and think about there's some notes on this model, and we'll think about the model a bit before we try and simulate it. Okay, so one interesting thing is that this is kind of in spirit of Anderson's original proposal of having singlets, right? Because what this interaction does is it wants the system to form singlets. Okay, but it's not that simple, because obviously if two sites form a singlet, then that site is committed to the other site, and there's another neighbor with which it cannot form a singlet. Okay, so it has to pick a neighbor with which to form a singlet. And that's why you wouldn't be surprised if you get this kind of wave function, because the system then has to fluctuate between all these states, because it's not happy picking any one neighbor. And so it could, now of course you could be concerned that of course it likes to pick a neighbor to form a singlet with, and so it could just form a static valence bond solid. Okay, and what I'm going to show you is that actually that doesn't happen in a certain set of models. Okay, so whenever we're given a quantum model, a simple lattice model, the first thing we want to ask about are what are the symmetries of the model. So a model has translational symmetry of the lattice, of course, a rotation, all the full symmetry of the lattice, and it also has an SON symmetry. Okay, so I can tell you about the symmetry is not too important for what I'm going to talk about, because I want to talk about the singlet phase. And it's very closely related to the SUN Heisenberg model. So in fact, if you take this model and put it on a bipartite lattice, it becomes exactly the SUN Heisenberg model. But here I'm interested in studying it on a non-bipartite lattice. And interestingly, this was never done before. Okay, so this is a very simple model which wasn't studied before. Okay, so let's think about the physics very quickly, which will help us understand what kind of ground states the system can have. So imagine that you take a certain wave function. Okay, so that's the color assignment. And so now imagine that I expand the singlet. So I have a singlet projector, and I have 1 on square root of n, so I have 1 over n. Then I have a sum on alpha and beta, and I have beta beta goes to alpha alpha. Okay, so what this says is that basically if you have any two sites which are neighbors, if they're the same color, they can switch to being a new color. Okay, so for instance, these two red sites are both red, And because they satisfy this condition, they could now become blue. But when they do this, then there's a new set of sides which have the same color. Okay, so these new set of sides now can fluctuate and become a third color, or in fact they can even, so remember it's also possible that alpha is equal to beta, and so you could actually stay at exactly the same color. Okay, so this is the quantum dynamics. You have this lattice and they have colors, and every time two sides are the same color, they can switch to a new color. Okay, so it's very, very simple. And so now we want to ask what kind of system will have the lowest energy. Okay, so this is of course a very complicated question, not one that we can answer simply, but we can understand that there are two competing tendencies in this model. And in fact, this is a very standard theme in lots of many body models, is that of course this, in some sense, this model, what it would like to do is it would like to make all the colors equal. Okay, because if all the colors are equal, then this Hamiltonian can act on every bond. Right? It can switch them, because remember the Hamiltonian only acts when a particular bond has the same color. So this Hamiltonian really likes it if everything is all equal. But of course, if everything is all equal, then nothing is in a singlet, because a singlet really requires you to be in an equal superposition of all colors. Okay, so that's the competing tendencies to form singlets. Okay, so there's a competition between forming equal colors, which is equal colors is like a magnet, right? If you have all your spins point the same direction, it's a magnet. And then there's this other tendency, which is to form a singlet, and these two things compete with each other. Okay, so now apart from thinking of this as a quantum problem, it turns out that for Monte Carlo simulations, like we discussed yesterday, you can map this to a classical model in one higher dimension, and it turns out that this model is very simple and it has a very nice geometric interpretation in its statistical mechanics form, sometimes called the Euclidean form. Okay, it turns out that it's basically just simply a model of tightly packed loops, and because this is a non-bipartite lattice, and this is a technical point I won't discuss, these loops turn out to be unoriented, and this turns out to be very important to understanding the physics. Okay, so I'll skip over this detail, but we can talk about it more later. And so, here it actually becomes very clear that if you have this gas of loops, if your number of colors are very large, the loops will want to be small. Because remember that there is an entropic gain. So if you have more colors, the more loops you have, the more independent color assignments you can make. And so as you increase n, the loops will want to become small. But when n is very small, the loops will become very large. Okay, and those large loops is exactly equal to having, like we discussed earlier, all these lattice sides have the same color. And short loops is exactly the same as forming a singlet. Okay, so now the interesting question we want to ask is, what is the nature of the singlet phase? Is it a solid or is it a liquid? Okay, in this model. Okay, so this is our latest paper where we studied this model on the Kagome lattice. And now, so basically, again, for n very small, we expect the system will go into a magnetic state. But as you increase n, at some point it will go into liquid state. Okay, so here's our data. This is for the magnetic order parameter. It's like the length of the loop, if you like. So when the loops are very long, it's like you have magnetism. You don't have to understand the details of this, but basically you have a finite value of the order parameter, and then at some value of n, this actually goes to 0. So that value happens to be 9. Okay, and there's different ways you can measure this, and you get a consistent result. So once the magnetic order is gone, the system is in a singlet phase, and now you might be interested in knowing, is this a valence bond solid, or is it a liquid? Okay, so this is the question that I want to answer now. And it turns out that there is a particular large n limit in which you can solve this model. So let me tell you briefly about the large n limit, and that will help us guess what the liquid state is. So it's based again on some earlier work by Arobas, Orbach, Reed and Sachdev and Ian Affleck, but we've adapted it now to this problem where you have non-bipartite lattices. Okay, so this is our model. So it turns out our model can be written as a bosonic Hamiltonian. This trick is sometimes called the Schwinger boson representation. And so this model can exactly be written in terms of bosons if you have this constraint that the number of bosons on every side is 1. So the bosons have n colors, and so if you have only one boson, then the color of the boson is the same as the color of the site in the original model. Okay, and so that thing that I described where two sites, neighbors, which are some color change to another color in the boson language just takes this form, right? Because you destroy two bosons with the same color and you create two bosons in their place with a different color. Okay, So this is just a rewriting of this model. But now there's something very interesting that you can do, is you can allow the number of bosons on a site to be different from 1. So when the boson number is exactly 1, you get this model. But now you can make the boson number 2, you could make it 3, you could make it 4. And this is like studying different representations of SON. It's very similar to how you study different representations of SU2, which we call spin, and that will be in the second part of the talk. Okay, so now we can ask, what is the phase diagram? So I showed you the phase diagram for number of bosons equals 1, and we saw that as we dialed up n, it began magnetic, and then at some point it switched over to being non-magnetic. So now our question is, what is this non-magnetic phase? So of course, we can't answer this question analytically. We'll have to return to numerics to do that. But what we can answer analytically is there's a particular large n limit. Okay, the large n limit, and I think this was introduced first by Arobas and Orbach, is that you increase the number of bosons you have on a site, you scale it up with n. Okay, so if you take that large n limit, and that coefficient is called kappa, then it turns out that you can actually solve this problem by standard saddle point approximations. Okay, and so this is the large n theory. It's a quadratic theory, and as you vary this parameter kappa, there are two phases. Okay, there's one phase where the bosons have a gap to creating excitations, and there's one where they condense. Okay, so now it's very clear that the phase that condenses is what we call the quadrupolar phase. It's the magnetic phase. It's the phase with long loops. It's the phase where all the sites have equal color. So this is the phase that we observed at small n in our model. So this is a large n approximation. Now if you decrease kb, the bosons get a gap. And so in this large n, it's just a simple gap state. But it's been known for a long time that you have to include 1 over n corrections to this theory to understand what the nature of the phase is. And beginning with Reed and Sachdev, it is known that basically the 1 over n corrections take the form of a U1 gauge theory. Now it happens in this particular model, because of this non-bipartite structure, this U1 gauge theory is coupled to matter fields with charge 2. Okay, and this is a problem that's been studied for a long time, originally by Fradkin and Shankar. They showed that this U1 gauge theory actually becomes a Z2 gauge theory. Okay, so I can talk to you more about this if you're interested. It's slightly technical, but the important point is that at large n you can show that this model has two phases. One is a quadrupolar phase and the other is a Z2 quantum spin liquid. Okay, so I'll talk about what this quantum spin liquid is. Okay, so we have answered this question of what the phase diagram is when we take both nb to infinity and n to infinity and we vary this parameter k. When this parameter k is large, you have this, what I call the quadrupolar phase. For historical reasons, it's called the quadrupolar phase, but you can think of it as a magnetic phase. And when this parameter is made small, you get a disordered phase, which looks like a Z2 spin liquid.
So, does this phase diagram hold for any kind of non-bipartite? So, or only for the Kagome or triangular?
Right, so the value of Kc that you get depends on the particular non-bipartite lattice you choose. But the general structure is independent. Question? Okay, so now if I put my Monte Carlo data, which is taken for NB equals 1, these green states were magnetically ordered, and these blue states were disordered. So now it's very natural that we should just draw a straight line over here and expect that these blue states are in the same state as the Z2 gauge theory, which you get at large n. Okay, so I'll show you that there's actually even proof for this. And if you just fix NB equal to 1 and you take the large n limit, it turns out this maps to a quantum dimer model on the Kagome lattice. And there's a well-known theory for a Z2 spin liquid on the Kagome lattice. So the simple extension of the phase diagram is that this model for n greater than 9 is in this spin liquid, Z2 spin liquid phase. Okay, so this is the last thing that we'd like to test. So what is a Z2 spin liquid phase? Okay, so a Z2 spin liquid phase is a phase in which has a gap to all excitations. And basically it has two varieties of excitations. One is called an E particle and one is called an M particle. It's like an electric and magnetic charge of a Z2 gauge theory. But in 2 + 1 dimensions, these are known to have anyonic statistics. Okay, so if you interchange two E particles, it's like not interchanging them at all, which is to say the E particle sees itself as a boson. So if you have an E particle and you take another E particle around it, it acquires no phase. And the same is true for m particle, but very remarkably, if you interchange an E and an m particle, you get a minus sign. Okay, so these are sometimes called neutral semions because the E particle sees the m particle as a pi flux when it goes around it. Okay, and so an interesting consequence. So, by the way, I took this from a review article by Laumann and Kail. And if you haven't learned this stuff, that's actually, I should maybe write it down if you're interested. It's a very, very nice article where all these things are pedagogically explained. And it's where Laumann and Kail. There were actually lecture notes on Kitaev's Lazouche lecture notes in 2009. So it's a great place to learn about some of this stuff. Okay, so then there was a remarkable set of work by Levin and Wen and Kitaev and Preskill, where they showed that having these excitations has a consequence on the ground state of a system in a Z2 spin liquid, which is its entanglement entropy has a correction to the area law. Okay, so if you look at the entanglement entropy, it has a leading area law and it has a constant negative correction to the area law. And for a Z2 spin liquid, you can compute this. It's a universal number. In fact, it's just log 2. Okay, and so Levin and Wen showed that, so this is unfortunately numerically a little awkward because you're trying to determine a number of order 1 from something which is scaling thermodynamically. And so you have to do some fitting and it's a little bit ugly. But what Levin and Wen showed is that if you actually compute the entanglement entropy on these interesting geometries and then you add and subtract them, you actually isolate this gamma completely. It's the leading piece. So the L dependence cancels completely out of all these terms. Okay, and so what we want to do now is we want to take our model on the Kagome lattice and implement this idea and measure the entanglement entropy. Okay, and so my student John DeMedio came up with a very interesting way to measure entanglement entropy. So I should say that there was great work by Roger Malko and Matt Hastings previously, which basically set the groundwork for John's work. But John really came up with an original idea. And so, again, I think I won't spend too much time explaining his idea to you. I think he should hear it from the master himself. But let me just briefly summarize the idea, just for completeness, and then we'll switch to looking at the results. So the idea is that, so first of all, the entanglement entropy, you can think of it, so this is an old trick, it's called a replica trick, as a ratio of two partition functions. Okay, so you can, so we're measuring the Renyi entropy, and so the Renyi entropy is a ratio of two partition functions, and one of the partition functions has weird boundary conditions. Okay, and if this is making no sense to you, just bear with me for 5 minutes. Let me finish this for people who understand what I'm saying, and then I'll come back to the data. Okay, so now what you have to do is you have to measure the ratio of partition functions with these very strange replica geometries. And what John did is he defined an ensemble of partition functions which interpolates between these two. Okay, so it has a new parameter lambda. When lambda is 0, it's this quantity in the numerator, and when lambda is 1, it's the quantity in the denominator. So if you want to measure the log of these ratios, all you have to do is you have to measure the difference in the free energy between lambda equal to 0 and 1. And that can be written as an integral of the derivative of this z function as a function of lambda. Now it turns out there's very convenient Monte Carlo estimators for this derivative. And so using them, if you integrate this from 0 to 1, you can actually compute this quantity gamma. Okay, so it turns out that this is very, very clever. And John wrote this up by himself this year. It's a very interesting way to measure the entanglement entropy. And so he actually went even beyond this and showed how you can relate this to some non-equilibrium protocols, but that's not important for our work. Okay, so here's our data for the entanglement entropy. As we increase it from n equal to 8, 9, 10, 11, you see that 8 and 9, this is a function of temperature, so I'm making the temperature smaller and smaller. These have a topological, this is just a topological entanglement entropy. So we've actually measured it for all these 4 weird divisions suggested by Levin and Wen, and we've constructed this difference. Okay, so this is very, very difficult to do. But by the way, in Monte Carlo, there's huge problems with ergodicity and everything else, because we're working with n equal to 11 colors and so. But he managed to do it for reasonable system size. He went up to n equal to 16. And here you see that when you cross this value of n, you actually get this quantized, this dashed line is the quantized value of the entanglement entropy.
Excuse me.
Yeah.
So, is this scheme independent on the? It does not require the periodic boundary condition.
No, it doesn't require periodic boundary conditions. You can do it for open, close, anything you like.
If there is no periodic boundary conditions, so you mentioned the onions and the topological Z2 phases that you said. You know, onions won't appear on 2D. Must be wrapped on a torus or something.
Why?
They can. That.
I mean, anyons are just excitations above the ground state.
Excitation, yeah.
So it doesn't matter whether you have
E and N charge on the 2D. They won't have that properties that you mentioned. When you change them, the minus sign won't happen.
Maybe we can talk about it later. My understanding of it is that doesn't really depend on the way you. So of course, when you have closed boundary conditions, you have some extra degeneracies in the ground state. But the statistical properties of the excitations are universal. They don't really depend on boundary conditions. But we can talk about it later. So anyway, so John showed very nicely, you know, that basically that you have this quantized contribution to topological entropy as you increase n, exactly at the same point where you lose magnetic order. And if you do finite size scaling, you see you get better and better quantization to this value. Okay, so this leaves almost no. This is basically not, you know, people keep criticizing spin liquids as having only negative signals, but this is clearly a positive signal and leaves no doubt that this state is a topological spin liquid. Okay, so just to remind you again that, you know, there are very few models we have for a Z2 topological spin liquid. Maybe the most famous one is Kitaev's toric code, which is exactly solvable. And I don't want to take anything away from these models because all these models are really amazing and beautiful. And I think Kitaev's toric code, if you haven't learned it, again, is there in that paper. It's a great model. One of its weaknesses, if I may say that, is that it has 4 spin interactions. Okay, so it's a little bit more complicated. And the same goes for Valence-Fisher-Gervin model, which is a model on the Kagome lattice, which also is known to give a Z2 spin liquid because this has 6 side interactions. Now, Kitaev's honeycomb model has only 2 side interactions, which is why you know, there's actually this realization in an experiment of Kitaev's honeycomb model in alpha ruthenium chloride. And it has very complicated interactions, and when he wrote it down, everyone thought that this was just a model of academic interest. But of course, in the last 5 years, it's become clear that it's important to understand various materials. And then the other realization is a quantum dimer model, which is actually not a spin model at all. It's a model of dimers. And in some sense, this is closest to the spirit of Anderson's resonating back. So it's not very clear where the valence bonds are in any of these models. But in this one, it's, you know, there are no spins, but there are, you know, this picture of valence bonds resonating is sort of captured. And so I'd like to advertise that this model is very simple. I mean, I guess the weakness of this model is that you have to make this number of colors very large, like maybe 8, 9 before you see the spin liquid. And so you could be concerned about how that could be realized in experiment, and I am too. And I'm hoping that you know, maybe one day we'll find a way, either cold atoms or real materials. But in the meantime, even if you're just interested in theoretical models, it's a very simple many-body physics model, and it realizes this Anderson's Z2 topological order. So I should say Anderson's RBB idea with Z2 topological order in a model in which you can really see how these singlets form. So in fact, this picture exactly applies to this model, except that this red singlet you have here shouldn't be thought of as up, down, minus down, up, but it should be thought of this as this equal color superposition. Okay, so that's the first thing I want to tell you about this model for a spin liquid.
What would be the difference between the designer model and the color code? You know, as I see, it's just like color code and Kagome lattice.
I don't know what a color code is. Is that some model in quantum information?
Yeah, it's by Bombine.
I don't know if that is true. Sorry. Maybe you can explain it to me later. There's a lot of things I don't know, but maybe you can tell me about it.
Yeah, but the degeneracy of your model.
The degeneracy.
Yeah,
On site or the
its
menu?
ground states must be degenerate somehow.
Oh yeah, I mean, of course in Monte Carlo it's hard to see these degeneracies because we're not doing spectral diagonalization.
Yeah.
But the belief is that if you take a Z2 topological state, it has a degeneracy which depends on the genus of the surface. So on a torus, it would be fourfold degenerate.
Not that actually.
Okay.
Okay.
Yeah, maybe you can explain.
Maybe if we want, just have a discussion about it, I think
Maybe
I have to explain the color code.
Yeah. Let's do it privately. How about
Yeah.
that? Okay, great. Okay, so now I want to get to my second part, which is about this interesting phase called the Haldane lemmatic. And so this is one. I'd call this a designer model because, in fact, we were motivated to think about this model because it didn't have a sign problem. And so now let me tell you another model that we were motivated to think about because to answer an interesting question. Okay, so you heard a lot about deconfined criticality. So if you take 2 plus 1D, you have spin half, you have a nail state, you have VBS state which has fourfold degenerate. And this critical point is very enigmatic. It's described by, there's two alternate field theories, the CP1 model and this West-Zumino-Witten model. And yesterday I showed you various evidences for both these things, and not all of it was my work, but many people here and in other parts of the world have studied this, and there's some consensus that something about this field theory is correct, and it may even be exactly close to what was originally suggested. But I don't want to get into this. But what I want to ask is something else, is imagine that you have a spin 1 nail state. Okay, so you imagine you have a square lattice and it has a nail state, and the spins are spin 1, not spin 1 half. Okay? So now suppose you try and increase quantum fluctuations and try and disorder it, what kind of ground state would you get? So now of course two spin 1s can form a singlet, and so the singlets can form a columnar VBS. So of course you could also get a columnar VBS. But it turns out that, so in fact we have a model in which we studied that, and that's known to be Nishita in fact studied it, it's known to be a first order transition. But if you think about the way, so remember the way that you destroy nail order in this is you proliferate topological defects of the nail order, right, which we discussed yesterday, hedgehogs. So what happens when you proliferate hedgehogs in a spin 1 system? Okay, so if you follow that field theoretic reasoning, you will not end up with a columnar VBS. Okay, it turns out, now of course we don't know what happens in a particular microscopic model, but at least we can answer in terms of the field theory. It's like, remember we discussed the XY chain, and when you proliferated vortices, you either got the Ising nail state or the VBS state depending on the sign of the fugacity, right? So over here now if you proliferate hedgehogs, it turns out that what you should get is something which I'll call a Haldane lemmatic. Okay, so this was originally argued by Reed and Suchdev. It's a very interesting state of matter. It says that you have these spin 1s, and we all know that in addition to forming two-side singlets, spin 1s in a chain can do something much more interesting. They can form so-called AKLT state, or the Haldane state, where it's not like two of them form a singlet, but a whole line of them forms a singlet. Okay, so this is a weird entangled, in fact we call it a SPT, state of matter. And it's a complex state and it has large entangled objects because the entire one-dimensional chain is entangled in some sense in the Haldane state. And so what could happen is, this is a very interesting way in which symmetry can be broken, is instead of forming simple two-side singlets like we saw in the previous spin liquid, and as we also know happens in the JQ model for spin 1 half, what can happen for spin 1 is that you form huge singlets and they form chains. Okay, so now these chains could be oriented in the x direction or the y direction, and so this particular singlet formation breaks the symmetry of the lattice, right? It breaks 90-degree rotation, and something that breaks rotation symmetry is often referred to as a lemmatic. Okay, so we call this the Haldane lemmatic phase. Okay, so Fa Wang, Donghai Lee, and Steve Kivelson, so this was originally proposed by Reed and Suchdev, and then they got interested in this because they said that it could be a model for magnetism in iron selenite. It's not something I'm going to talk about very much. But they also suggested that the phase transition between this nail and the Haldane lemmatic is some very exotic field theory. Okay, it's a O4 model with the topological term. You can also think of this as, again, the two different ways you can think about it, either as a gauge theory or you can think of it as a topological field theory. So they had both these suggestions, and the question is, does this really happen? Okay, so as we all know, for spin 1 half, Anders' JQ model really convinced a lot of people that this deconfined criticality story actually happens in a model. So now the question is, can we find a model which realizes this transition? Okay, so of course we know a model that realizes the nail phase. It's just the Heisenberg model, but we need with spin ones. But we need now a spin one model that realizes this Haldane lemmatic. Okay, and so that's what I want to tell you about in the second part of the talk. Okay, so we need a model which has spin 1 and doesn't have a sign problem. We all know the Heisenberg model doesn't have a sign problem. For any value of spin, that's very easy to prove. It satisfies Marshall sign theorem. But how do you go beyond the Heisenberg model? Because we want to tune something that destabilizes the Heisenberg model. And it turns out it's actually not so easy. So, I mean, of course, you can use Anders' trick and construct a Q term. But the Q term turns out, the more classical the spins become, as you make S larger, it doesn't do much to the nail state. So we need to go beyond it. And it's hard to think of the sign problem in terms of these higher spins. Okay, so there are some exceptions, and there's this work by, again, Naoki and Kenji, where they showed the biquadratic interaction doesn't have a sign problem. Okay, so it turns out that this biquadratic interaction doesn't create the Haldane lemmatic. And so we need something else. Okay, so basically what I'd like to do before I discuss the Haldane lemmatic is we need a general strategy to create sign-free, rotationally symmetric spin-S models. Okay, so basically we have this JQ model, and now we want to try and find ways to write more general models for spin-S. Okay, so that's something that we succeeded in doing. And we use an idea that, again, was pioneered here in Japan by Todo and Kato, based on earlier work by Kawashima and Kubernetes. And there's a nice review article you can read about. So the idea is simple, is that you basically, if you have a spin S, what you can do is you can write it as a sum of 2s spin 1/2s. But when you do that, you have to introduce a symmetrization operator. And the way that works in Monte Carlo is this affects the boundary conditions of the spin. And so basically, pictorially, what you can do is you take every spin at side I and you replace it. So say you want to do spin 1, you replace it by 2 spins. So there's another index A. A is 1 or 2, corresponding to 2 spin 1/2s. Okay? And so, for instance, if you want to do the Heisenberg model, pictorially, it will look like you take 2 sides. And now what you do is that you have spin half models over here. And these spin half have a Heisenberg interaction with each other. Okay, so now what you have to do is that, so if you're just simulating 2 sides, you have to consider all of these 4 configurations with equal probability. Okay, and so then you can do Monte Carlo sampling. And so now the nice thing is that because P doesn't create a sign problem, if the model doesn't have a sign problem in this, if you can call this a split spin or the mini spins S, then the capital S model doesn't have a sign problem as well. Okay, so for instance, if you want the model of Kenji and Naoki, it looks simply in this picture like this, right? You have 2 interactions between spins. So now we realize the strategy that we should have basically is that rather than writing these spin models down and trying to draw these diagrams, it's much easier to draw the diagrams first. Okay, and then you can work backwards and guess what models don't have a sign problem. And so interestingly, so these of course were known to not have sign problems, but now we can write very complicated interactions. And we have very simple algorithms, because the algorithm here is just the algorithm for the spin half Heisenberg model, which, okay, if you do these things, is a very trivial algorithm. Okay, so this makes the whole procedure very simple. And this again was done by my student Nishita, who's over here. So for instance, you can have 3 spins. And now there are many diagrams, and I've just drawn one of them, where you have these spin 1/2 interactions between 3 spins. Okay, so now if you take all these diagrams, sum them up, you can write this in terms of spin 1 operators, and then it has this very interesting form. So the thing is that you could have never guessed, if you just given spin 1 operators, that this model doesn't have a sign problem. Okay, it would have been very hard to guess, but in this language of split spin, it's very simple. Okay, so so now what we can do is we can take these are 3 spin interactions. So this is, we're getting deep in designer land. I mean, we're not trying to model any experiment here, we're just interested in models which are spin rotation symmetric with a spin 1 Hilbert space, which have the symmetry of the square lattice. Okay, so to make it have the symmetry of the square lattice, what we do is we make plaquettes, 3x3 plaquettes of these interactions. And so this is like Anders' JQ idea. Basically what you do is that you combine this interaction, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1, 4, 7, 2, 5, 6, 3. So you have these interactions. Okay, so now what we can do is we can study an interesting model. This is the Heisenberg model, and this G is a new tuning parameter for this 3x3 interaction. Okay, so now let's not worry too much about the fact that remember again by universality, it's a local interaction and it preserves all the same symmetries as the Heisenberg model. Okay, so it's just an interesting tuning parameter for us. And I'm going to now prove to you that this is the interesting phase diagram of this model. Okay, so this model has a Néel state for small g, which is no surprise because we know at g equal to 0, it's a Néel state. This doesn't survive finite temperature. But now I'll show you that when you increase g at some point, the system goes into a Haldane nematic phase. Okay, and the Haldane nematic phase breaks a discrete symmetry. In fact, it's an Ising symmetry because it can be either x or y. And so you expect there's a finite temperature phase transition. And we'll study the finite temperature phase transition as well. Okay, so now, okay, so basically we need order. So first of all, we want to rule out that when Néel order is destroyed, there's not just simply a columnar state because that's always a possibility. And so we have to create order parameters for this state and this state. Okay, and so what we do is you define a bond operator, and the columnar order parameter is just a standard one. You Fourier transform the bond operator to pi 0. And that's a variable we call phi. But there's another variable you can define. And actually afterwards we found out that this was also done in a different context by Professor Kawashima and Professor Harada. And basically what you do is you take bx minus by. Right? So basically if this quantity is positive, it means the bonds are oriented in the x direction. If this quantity is negative, it means the bonds are oriented in the y direction. And you sum it over the entire lattice, and this forms an order parameter for the Haldane nematic. So if we truly have a Haldane nematic phase, this order parameter should be finite, and this order parameter should be 0. Okay, so we can now do finite size scaling. So I've marked all these points, H, I, J, K, L. These are points in my phase diagram, or I should say Nishita's phase diagram because she did everything. I was just the cheerleader, as they say in America. So anyway, so if you take H and I, clearly the magnetic order parameter is finite. And if you take J, K, and L, you can see the magnetic. So this is just a conventional linear order parameter. I didn't bother defining it. It goes to 0. Now you can look at this Haldane order parameter. And interestingly, in J and K, the Haldane order parameter is finite. You can see that as you go from J to K, it gets smaller, as you expect, because you're crossing a phase transition. And when you reach point L, it's 0. Okay, and if you measure the conventional BBS order parameter, it's just 0 everywhere. So the system is very convincingly in this Haldane nematic phase. Okay, but now we're ready to go and answer this interesting question. So Deng-Hai Lee, Steve Kibelson, and Fa Wang came up with this theory that this transition could be O for a model at theta equals pi. And so now we have actually for the first time a model in which we can test whether this idea is true. And if it's true, of course, it's very exciting. It may explain high temperature superconductivity, or maybe not. But let's study this. Okay. So the first thing is we can study the phase transition in this regime, and so we have very nice data that this phase transition is just a conventional Ising thermal phase transition. So we can study very large lattices. We have nice data collapse with Ising critical exponents. If you look at the histograms, you see that there's no coexistence, right? So at high temperatures, there's one peak. This is just classic Ising model, right? At high temperatures, there's one peak, and as you cross the phase transition, there are two peaks which get split more and more as you cross the phase transition. So no surprise. But now we can go to this red line, which is at very low temperatures, and unfortunately, what we find is that there's very clear evidence for phase coexistence in this regime. Okay, so we conclude basically that this star point is not this exotic critical point, rather it is a first order phase transition, and this first order phase transition apparently weakens, and then at some point it becomes continuous. And this is very well known to happen in the Ising model. It's called the tri-critical Ising model. There's a classical StatMech model called the Bloom-Capell model where the same thing happens, and you can study how first. So I mean, in principle, we can study that in this model, but our main interest was to. So we have a continuous transition, which we showed as continuous over here, but starts to become first order and then remains first order at 0 temperature. Okay, and it turns out actually that even before this, I should say that I even wrote to these people when they wrote their paper that there's a concern that this field theory does not have a continuous transition because we know another model which realizes this CP1 with double monopoles, which is the rectangular deconfined criticality. And that's something we studied previously, and we knew that it was first order. But I mean, of course, here the symmetry, the Z2 symmetry breaking is not a symmetry of translation like it is in the rectangular deconfined criticality. Here it's a rotational symmetry of the lattice. So it was possible that something would be different, but it turns out not to be the case, and we have a first order transition. Okay, so so this, to summarize the second part of the talk, is that we have a nice, relatively simple, it's maybe not as simple as we would like, sign problem free model to realize this Haldane lemmatic phase. And it's actually a very interesting phase in itself. I mean, just like the VBS is a very interesting phase, in some sense this is a more exotic form of VBS because the singlets are not two-side singlets, but they're already extended sub-extensively across the system. Okay, so this is an interesting phase, and now we have a nice model, so we can study this phase, and we can, there's lots of interesting things. For instance, you can ask what happens if you put an impurity in this phase. What happens if you add disorder? Does it form a spin liquid? Because the system is almost like a spin liquid because these singlets are getting very long. And so there are many interesting questions you can ask. The first question we were able to answer is the nature of the phase transition between these two phases, which we found is first order. Okay, and so of course, this was supposed to be just one application of this actually idea that we developed, that was originally developed by Todo and Kato and also Kawashima and Gubernatus. And so now it's very interesting because we can study disordered phases with spin larger than 1/2. So there's all kinds of interesting phase transitions. So already for spin 1 you see that you have more than just Nail and VBS. You also have the Haldane lemmatic, and you can also have a quadrupolar phase. There's all kinds of things you can have, and there are phase transitions that they're interesting phase transitions which we don't understand in these quantum systems. And so now we have models to study them, and we can hopefully make connections with the field theories that describe these states. Okay, so that's all I have. Thank you. Yeah.
So in the first part of your talk, I think you didn't mention what is the nature of the magnetic to Z2 spin liquid phase transition?
Yeah, that's a very good question. Yeah. So so there is an understanding, at least from field theory, for how this transition should be. We've tried to simulate it. So of course, this model we study only for discrete values of n, but of course we can make various design uncouplings to go across the phase transition, and we've done that. Part of the problem is it's very hard to equilibrate this VBS phase. Oh, sorry, the spin liquid phase. Because it's a spin liquid, there are huge problems with autocorrelation, and it turns out that on the triangular lattice, well, actually no, the problem exists even on the triangular lattice. So the field theory, though, I can tell you what it is. There's an expectation for the field theory, and we hope one day that we can test that.
So it's a continuous transition, should be?
There is at least a field theory that says it's continuous.
So it's a sort of deconfined critical point? Or?
Yeah, it's a deconfined critical point, but it's a very simple example of a deconfined critical point. So so what happens here is that so this is a slightly complicated Z2 spin liquid. Because remember we discussed the Z2 spin liquid has an E and an M particle, and typically the E and M particle don't carry any internal symmetry. But here, because this model has SON, the M particles actually have SON symmetry. And so the Z2, so when you're in the Z2 spin liquid, you have the M particle which carries SON symmetry, and the formation of magnetic order actually corresponds to the gap of this particle going to 0. And so the M particle condensing. So remember, the M particle can't condense itself because it has these non-trivial statistics. So only bosonic quantities typically can condense. And so what condenses is a bilinear of the M particles, which is exactly the quadrupolar phase. That's why it's called a quadrupolar phase. So the theory is basically what Senthil would call an ON star transition. It's sort of like an ON transition, but what's condensing is not the fundamental order parameter, but a bilinear order parameter. But yeah, it'd be very nice to study that and see that. And for instance, it'd be very interesting to understand the scaling of entanglement at the critical point. And hopefully with John's method, all of this will become accessible now. So we're very excited to study all these things. And so there's also a transition from the spin liquid to a VBS, which actually we're able to study on the triangular lattice. That's also one of these kinds of phase transitions. Yeah, and I want to say, because I remember reading, so I should say that, Kawashima, Harada, and Troyer first studied this model on the bipartite lattice. And there was a previous paper, I can't remember by whom, that claimed there's a spin liquid between the two. I think one of the main results of that paper is that spin liquid doesn't exist. And now, as far as we know, on bipartite lattices, these models don't give spin liquids. But it's interesting that actually this idea of a spin liquid emerges if you study exactly the same model, but not on a bipartite lattice. So on a non-bipartite lattice, then the spin liquid emerges in between them. Sorry, you had a question?
Oh yeah, so if you actually, for the second model you were talking about,
Yeah.
if you actually find a second order phase transition with a designer Hamiltonian, by universality you can sort of argue that it should be the same. But I'm wondering if you actually get a first order transition, should we expect that that's also universal in some sense? Because,
Yeah, it's a very good point. Yeah, so it's not, of course. So, I mean, as often argued, that basically any model can become first order.
yeah.
But at some point, so of course, this is the first model in which we're studying this. So, maybe, but actually that's not true, because as far as the field theory is concerned, this field theory, in some sense, is as I said, it's actually this field theory with exactly these anisotropies is actually realized in the rectangular lattice. So if you take deconfined criticality and you make the system rectangular, so imagine that you take the deconfined critical point and then you start making the x direction and y direction slightly different.
Okay.
Then, so if you study the transition between this deconfined critical and you add this lambda rectangular to this, then the phase transition between nail and the VBS is now twofold, right? Because you have rectangular lattice.
Right.
This phase transition is described by exactly the same field theory.
This field theory.
Yeah.
Oh.
The either of these CP1 plus double monopoles and O4. So it's very different, the VBS here, but it turns out in the field theory they're basically the same.
I see.
And it turns out that this one also has a first order transition. It also turns out that this O4 model at theta equals pi is supposed to describe the easy plane model with a slightly different O2 cross O2 anisotropy. But it turns out that easy plane model also seems to have a first order transition.
So you're saying
So-
that, but when you say it's known that they're first order, you mean numerically?
Numerically, and so of course there's no way to prove that. So you can only, if you have a continuous transition, then you can be happy. And of course, again, numerically you can't even actually prove anything is continuous because you can only simulate a finite size. So you have that problem as well. But if you can't find any model which realizes a continuous transition for a particular field here, at some point you have to just say that
I see.
it might be first order.
I see.
So, yeah, but you're right. I mean, you can't use universality once you have a first order. It's hard to apply.
So is it possible to reduce the n at which this spin liquid phase in the first part appears by some other interactions?
I'd love to do that, yeah. So, I mean, I think that's, I tried to do that. I tried putting the Q term, actually. And then so actually I didn't do it on the Kagome lattice. I did it on the triangular lattice. And then what happens when you put the Q term is you just get a first order transition to VBS. In fact, it forms a very interesting root 12 cross root 12 VBS on the triangular lattice. I didn't present those results. That's there in this original paper. But yeah, I mean, if you have ideas or anybody else has ideas, I'm very interested. I mean, because I think that, yeah, it's good. I mean, there's no fundamental reason why it should happen at such a large value of n, but so it's very interesting to think about that. And of course, that would make it more realistic. I mean, of course, the nice thing about it is it's a very simple model. So of course, we'd complicate it, but then you'd get it at smaller values of n.
Kind of connected to that question, but do you have an intuitive explanation why n equals 9 is different from n equals 8?
It's larger.
It is large too.
Yeah. I think that so one thing is to prove that this model actually you can show. Is that if you fix n equal to 1 and you make n very large, this model actually, so at n equal to infinity, if you fix, I took a particular n equal to infinity limit where I made the number of bosons large as well. if you fix the number of bosons to 1 and you just take the n goes to infinity limit, it maps to a quantum dimer model.
Right.
And it's on the same lattice, the quantum dimer model, as the original model. And it's known now from the work of Mosna and Sondi and Miskish et al. That quantum dimer models on these non-bipartite lattices realize Z2 Z-confined phases. So in some sense, increasing n puts you closer and closer to a quantum dimer model. Of course, the quantum dimer model can also VBS order. In fact, that's what happens in the triangular lattice, but that's a separate story. But basically, so that's one reason why n may need to be larger now. But but again, on this question is a good one. It's not universal in any way, 8 or 9. So it's conceivable that some other lattice, this could be smaller.
I think the original paper by Affleck gives some sort of intuitive argument that as you go to larger n, then forming singlet becomes more favorable.
Yeah.
There is a very simple argument. Just counting numbers of configurations.
Right. So it's like this entropic argument we're making that when n is larger, the system wants to go. Basically what you could do if you wanted a very simple variational argument is you could just take this Hamiltonian, and there's two simple variational states. One is where all the guys have equal color, and you can calculate the average of the Hamiltonian in that. And the other is where every state is basically in a dimer state. So every bond that's, of course you can't put every bond in a singlet, but you can put some fraction of the number of bonds in singlets, right? And then you can take the average of the Hamiltonian in that. And n appears because this is 1 on square root of n. And so the balance between those two states actually depends on n. So when you make n large, the singlet state will be low in energy. Of course, this is a very cartoon state because the singlet state could be a VBS, it could be a spin liquid, there are many things it could be. But at least it shows you that when you increase n, I think maybe that's the kind of argument, that it favors the formation of a singlet. But when n is small, it basically just wants to have all equal colors so that it can fluctuate. Every bond can fluctuate.
Oh, so it's about the second part. So you try the model with s equals 1. So I know that so if you try a higher spin like 3/2, I think you could have a 4/4 degenerate state.
Yeah. So
right?
that's
So have you tried that, or do you plan to do that? I'm very curious about the result.
Yeah, even I'm very
transition
curious. So Nishita and I talked about doing that. I mean, Nishita's doing many things. So I think there's many interesting things you can do with higher spin. But one of them is the fact that, just like in one dimension, there's this even-odd effect of the Haldane gap.
Mm-hmm.
That, even spins have, integer spins have Haldane gap, and odd integer spins are in the gapless state.
Yes.
There's a periodicity over here as well.
Yeah, it's 2D, I think the periodicity is 4, right?
On a square lattice, yeah. So it's so spin 3/2 is the same as spin half, but spin 1 is not the same as spin 2.
Mm.
So yeah, we studied spin 1 case, and I think the next thing to do is to spin 3/2. And
I see. So you actually plan to do that?
yeah,
Okay.
Yeah.
Good.
we can do it together.
So for all these models you designed, they all satisfy the Marshall sample, is that correct?
That's correct. Yeah. So I mean, there's another class of models which don't satisfy Marshall-Sine rules, which are constructed from fermionic operators. And in some limits, the fermionic operators also give spin models, and some of those spin models don't satisfy Marshall-Sine theorem. They form representations of SUN that don't. But the ones I spoke about today all satisfy Marshall's. So that's the most trivial way to satisfy the sign problem condition, is to make sure that the model satisfies Marshall rule. Then in the basis in which it satisfies Marshall's rule, if you construct a path integral, you'll have positive weights. Yeah, there's two exceptions. One is the so-called Meron cluster algorithms. There's a particular way to solve the sign problem for certain models that don't satisfy Marshall sign theorem. And the other models are models which are constructed out of fermions, like Hubbard models, with determinantal Monte Carlo. And some of them don't have sign problems, even though they don't satisfy Marshall sign theorem. So those are two exceptions. But everything I spoke about today satisfies Marshall sign theorem. If you want to use this path integral Monte Carlo, Again, with the exception of the Meron cluster, there's work by Visa and Chandrasekharan on Meron cluster algorithms, but with the exception of that, all the models we know all satisfy Marshall sign rule. So our designing is limited to designing models without Marshall sign theorem. We satisfy Marshall sign theorem.
This is not a question, but I have a comment on the second part. Actually, Philip Pomper and his colleague consider the effect of biquadratic interaction in the string one system, and they seem to find a similar phases.
Yeah.
Yeah. So maybe it's related.
Yeah, no. So we of course we cited that paper in our publication. I didn't mention it today because it was not completely related to. I mean, so there are many other people, but Philip Pomper used tensor networks to study the bilinear biquadratic model, I think, on the square lattice. And they claim that in 2 dimension, there's a very small window in which it does exactly the same thing. I mean, he wrote to us saying that he wasn't able to resolve whether it's first order or continuous using his method. So I should say, yeah, maybe I should maybe add a little bit here that, of course, when I said that Wang, Kivelson, and Lee studied this Hallian nematic. Of course, there are many other people that also studied it. I mean, these people may be popularized in recent times, but there's also DMRG work by Donna Sheng and Joel Moore in a particular J1, J3 model in which they claim this exists. And then there's a work by Carlo and his collaborator. Thank you. Thanks for pointing that out.
No further questions? Okay, thank you.